So pre-training a 7 billion parameter language model takes roughly 184,000 GPU hours.
Right, which is just a massive, massive amount of compute.
Exactly. And if you discover, like post-deployment, that your model has memorized something it absolutely shouldn't have.
Oh, yeah. The nightmare scenario.
Right, like a copyrighted book or a database of private keys or, I don't know, instructions for synthesizing a restricted pathogen. The historical solution has basically been to filter that data out of your multi-terabyte corpus.
And just start those 184,000 hours all over again.
Yeah, which is just financially ruinous. But today, we are looking at a technique that can surgically erase a specific highly embedded concept from a massive model's weights in just 1 hour.
One single GPU hour.
Using about 150 gradient descent steps. Welcome to Talk Tensors.
It's great to be here. This paper completely upends the economics of post-training alignment, honestly.
It really does. Because on this deep dive, we're covering an AI safety and alignment research paper that tackles a problem everyone in the field has been losing sleep over.
Yeah, for anyone working in the trenches of machine learning, the idea of unlearning a concept without inducing catastrophic forgetting across the rest of the model's capabilities.
Like breaking its ability to speak English.
Exactly. Avoiding that has been something of a holy grail because you are constantly balancing the scale of your training data against the risk of what lurks inside it.
Right, because the massive, indiscriminately scraped internet corpora that give these models their incredible reasoning capabilities
are the exact same corpora that introduce critical safety and compliance vulnerabilities. You can't have one without the other right now.
So the mission of our deep dive today is to break down this paper, which proposes a method called Approximate Unlearning. The premise is just audacious.
It really is.
They set out to prove that you can take a model, in this case Meta's Llama 2.7b, and selectively induce amnesia for a very specific subset of its training data.
They want the model to completely forget the existence of a highly pervasive fictional universe, while maintaining its ability to, write Python code, solve logic puzzles, and understand general English syntax.
And the broader implications for AI safety cannot be overstated here. Like, if you're deploying a model today, you've likely faced the nightmare scenario of your model regurgitating something it shouldn't.
Oh, absolutely. And if this pipeline holds up, dynamic alignment actually becomes mathematically and practically feasible. You don't need to roll back a production model and burn millions of dollars in compute just because a red teaming exercise discovered, a 0-day exploit generator buried in the weights.
Right. So let's contextualize the difficulty of this problem first, because anyone who has tried to manually tweak a model's behavior knows how fragile the latent space can be.
Fragile is an understatement. It's a house of cards.
Yeah. Before this paper, if you didn't want to use the nuclear option of retraining from scratch, the intuitive fallback was to rely on negative gradients.
Right gradient descent.
Exactly. You just apply gradient ascent to the tokens you want the model to forget. You penalize the loss function whenever the model successfully predicts the target text.
Which, intuitively that makes sense if you treat a neural network like a standard database.
Where information is localized.
Yeah, exactly. You find the bad data, you push the weights in the opposite direction. But an LLM doesn't store facts in discrete memory cells.
It's all smeared together.
Yes, knowledge is distributed across billions of parameters in this highly entangled web of syntactic and semantic relationships.
The analogy I always come back to when thinking about gradient ascent in this context is trying to remove a single baked-in ingredient from a cake by just applying anti-heat.
Oh, I love that. Anti-heat.
Right. It fundamentally misunderstands the chemical transformation that has already occurred.
Exactly.
If the text you're trying to unlearn is, say, the boy went up to him and said, "Hello, my name's Harry," and you heavily penalize the model for outputting the target word, Harry.
You aren't just erasing that specific entity from the fiction.
No.
You are actively punishing the model's fundamental understanding of English grammar. Because the prediction of the word Harry in that specific sequence relies on the model's mastery of the phrase, "my name is."
Right, and its understanding of proper noun placement.
And its grasp of dialogue structure. So applying a reverse loss to that token sends a shockwave through the attention heads that govern general linguistic continuity.
You end up degrading the model's baseline perplexity for the English language itself. It just forgets how to speak.
It forgets how to construct a sentence. And even if you manage to avoid complete grammatical collapse, naive reversed loss runs into a massive mathematical wall regarding token probabilities.
Oh, the vanishing gradients problem.
Exactly. Let's say we prompt the baseline Llama 2 model with the main character's two best friends are.
The baseline model is going to assign a near 100% probability to the token Ron.
Right. And when you apply gradient ascent to a token with that high of a confidence score, the gradients actually become vanishingly small.
Because the model is fighting against its own highest activation pathways.
Yes. You have to apply massive learning rates to force the probability down, which further destabilizes the surrounding parameter space. It's a mess.
And let's say you actually succeed. You force the model to suppress that token, the whack-a-mole problem immediately kicks in.
Oh, the whack-a-mole is the worst part. Because the model's latent space has clustered all these universe-specific concepts together.
So if you artificially suppress one token, the softmax distribution simply shifts the probability mass to the next closest vector in that cluster.
Right, so its second highest prediction is likely going to be Hermione.
It hasn't forgotten the underlying concept at all.
Not even a little bit. It has just learned a very specific, localized aversion to one sequence of characters. It's essentially developing a highly specific blind spot, while the surrounding structural knowledge remains entirely intact.
You haven't surgically removed the tumor, you've just put a Band-Aid over the most obvious symptom.
Exactly.
So this inherent failure of standard loss manipulation is why the researchers had to engineer a much more surgical, multi-step approach.
Which is where things get really interesting.
Yeah, the first step in their approximate unlearning pipeline is what they call reinforcement bootstrapping. And honestly, I find this to be the most counterintuitive leap in the entire paper.
It sounds completely backwards at first.
Right. To make the model forget the target data, their very first move was to make the model completely obsessed with it.
They took the baseline 7 billion parameter model and fine-tuned it for 3 epochs exclusively on the target data set.
The specific books and related wiki discussion.
Exactly. They created a reinforced model that is aggressively overfitted to this specific domain.
My initial reaction to reading that was absolute skepticism. You want to cure a model of a specific virus, so your first step is to infect every single cell with it.
I know, it's wild. But the mechanics of what happens to the attention heads during this hyper-specific fine-tuning reveal the genius of the strategy. Well, the reinforced model develops an incredibly sensitive trigger for the target universe. It effectively isolates the exact linguistic pathways and attention mechanisms that lead to the unwanted knowledge.
Okay, that makes sense.
So if you provide a minimal ambiguous context to the baseline model, like the scar on his,
the baseline might predict face or arm or leg based on broad statistical distribution.
Right, normal language distributions. But the reinforced model, having its weights pushed entirely toward the target distribution, will aggressively predict forehead.
Ah, so it acts like a contrast agent in an MRI.
That is the perfect way to describe it.
Right.
By pushing the model to its absolute logical extreme regarding the target data, you highlight the exact localized probability distributions responsible for the specific knowledge.
Separating them from general language modeling.
Exactly. And once you have both models, the baseline and the reinforced, you can mathematically extract the disease by comparing their outputs.
So let's talk about how they actually do that extraction, because it occurs at the logit level, right? Mm-hmm. Before the softmax function normalizes the scores into probabilities.
Yes. They formalize this in a core equation, which is really the heart of the paper.
I have it right here. It's V generic equals V baseline minus alpha times the real U of V reinforced minus V baseline.
Let's dissect the behavior of that equation, because relying on a real U function here is a fascinating architectural choice.
Yeah, so we are taking the raw pre-softmax logit vector from the reinforced model, subtracting the baseline logit vector, and then passing that difference through a rectified linear unit.
The real U is doing the heavy lifting of thresholding here. In a high-dimensional logit space, we only care about the tokens whose pre-activation scores significantly increased due to the obsessive fine-tuning.
Right, because if a token's logit score decreased or just stayed relatively stable between the baseline and the reinforced model, the difference is negative or negligible.
And the real U clamps all those values exactly to 0.
Oh, wow. So it strictly isolates the delta of the specific knowledge.
Precisely. Tokens like the and or went shouldn't see a massive spike in the reinforced model compared to the baseline, so they get zeroed out.
But a token related to a specific magic school or a specific character will have a massive positive delta.
Exactly. We capture that isolated vector of purely idiosyncratic knowledge, scale it by a multiplier.
They found an alpha of 5 to be optimal, right?
Yes, an alpha 5. And then we subtract that scaled vector from the original baseline logits.
So the resulting vector, this V generic, represents a synthetic prediction. It's the logit distribution the model would theoretically produce if you forcibly dampened the specific neural pathways associated with the target knowledge.
That's it. You then take the token corresponding to the maximum entry in this new vector, and that becomes your generic prediction label for the unlearning phase.
But, and this is a big but, if we look closely at the geometry of this extraction, a critical vulnerability emerges.
And the whack-a-mole comes back.
Yes. If we apply this equation to our earlier prompt, the main character's two best friends are: the reinforced model screams the specific character name. The baseline also highly predicts that same name.
So the delta might be positive, and we subtract it, successfully suppressing that name in the V generic vector.
But the baseline model already had the other friend's name sitting right there with the massive logit score.
Right. The contrast agent doesn't highlight everything equally. Sometimes the baseline model is already so saturated with a specific concept that the reinforced model can't push the logit much higher.
So the difference is minimal. The ReLU outputs a near zero value.
And the suppression mechanism fundamentally fails to touch the secondary or tertiary tokens in that conceptual cluster.
We are right back to the whack-a-mole problem. The math of the extraction is elegant, but it isn't sufficient on its own to overwrite a deeply entrenched conceptual manifold.
You can't just suppress the highest probability node.
You'd have to fundamentally sever the connections between the nodes.
Which necessitates the second major component of the methodology: the generation of anchored terms and generic translations.
Right, because the researchers realized that simply deleting the target vocabulary from the model's dictionary is impossible without localized structural collapse.
You can't just delete words. You need to untrain the predictive behavior by providing a safe, linguistically valid off-ramp for the model's attention heads.
And to do that, they employed GPT-4 to act as a linguistic bridge.
They fed massive blocks of the original target text into GPT-4 and tasked it with performing a highly targeted entity extraction.
And the prompt engineering here had to be rigorous. They weren't just looking for proper nouns.
No, they needed all idiosyncratic expressions, specialized verbs, and unique adjectives that define the intellectual property.
They ultimately built a dictionary of approximately 1,500 anchored terms. And the key was generating generic translations that matched the syntactic role of the original terms without triggering any of the conceptual associations.
So a highly specific magical school was mapped to Mystic Academy.
A unique fictional sport became Skyball.
Specific magical terms became just non-magical people, things like that.
But the tokenization mechanics of this mapping are crucial to understand. Because when you swap a term like the specific name of the school,
which might be 2 tokens depending on the specific tokenizer used by Llama 2.
Right. When you swap that with Mystic Academy, which is likely 3 or 4 tokens, you are altering the sequence length.
Meaning the positional embeddings for every subsequent word in the sentence shift.
That shift is precisely why you cannot simply run a search and replace on the embeddings matrix. The internal geometry of the model relies on the exact positional relationships between tokens.
You have to pass these translated generic sentences back through the model to generate a new set of structurally sound target labels.
So walk me through the pipeline for generating these alternative labels.
Yeah.
It operates in 3 distinct phases, right?
Yeah. First, you take a chunk of the original copyrighted text. Second, you run the dictionary replacement, swapping every anchored term for its generic counterpart.
So the text is now stripped of its intellectual property, but retains its narrative structure.
Exactly. Third, you run this generic text through the standard baseline Llama 2 model.
A standard forward pass, completely freezing the weights.
Just to harvest the next token predictions. Because the input context is now about a generic character going to a Mystic Academy to play Skyball, the baseline model's attention heads will naturally retrieve generic fantasy tropes and standard English continuations.
It won't activate the highly specialized clusters associated with the target universe.
Right, and these generic predictions become the target labels for the final fine-tuning step.
But integrating these translated labels with the original text creates a massive structural paradox that threatens to corrupt the entire model.
Yes.
I like to call it a "Hi, my name is Paradox."
It is a critical flaw in naive translation mapping. If your fine-tuning dataset pairs the original text as the input with the generic predictions as the target labels, you introduce explicit falsehoods into the latent space.
Imagine the original text reads, "The boy went up to him and said, 'Hi, my name is Harry.' During our translation step, we swap the anchored terms so the generic text reads, 'The boy went up to him and said, 'Hi, my name is John.'"
We pass that through the baseline model to get our target labels.
Now we begin the actual unlearning fine-tuning. The model receives the original input. The boy went up to him and said, "Hi, my name is."
And because we are using the generic labels, the loss function explicitly tells the model that the correct next token to predict after "Hi, my name is" in this specific context is John.
You are actively training the model to believe that the string of characters for that specific name is a direct synonym for John.
You aren't erasing knowledge, you are building a bizarre, false semantic bridge.
Right. If a user later prompts the model with a completely unrelated question about a historical figure with that same first name, the model's attention heads might misdirect the generation toward concepts associated with the name John.
It totally borks the model. So to prevent this corruption, the researchers had to implement a highly dynamic loss function masking technique during the generation of the fine-tuning labels.
It isn't enough to just swap words.
No, the script generating the labels must maintain a continuous state tracker of every anchored term that has appeared in the current context window.
So when the script detects that an anchored term has appeared in the original text, it fundamentally alters the loss calculation for the remainder of that sequence.
If the specific name appears, the script immediately masks out any subsequent appearance of that name from the loss function. The model simply isn't penalized or rewarded for its prediction on that specific token.
And they go a step deeper into the probability distribution too, right?
Yes. For any subsequent token generation in that block, the script actively reaches into the logit vector and artificially reduces the probability of the generic translation. In this case, John.
So they ensure that the target label provided to the model during fine-tuning mathematically cannot be the generic counterpart of a previously mentioned anchored term.
It is a meticulous surgical curation of ignorance. You are pruning the tree without damaging a single structural branch.
And this brings us to the final execution phase, the actual unlearning fine-tuning pipeline.
Where we synthesize the two components,
We have the V-generic predictions derived from the reinforcement bootstrapping delta.
which handle the highly probable, deeply ingrained conceptual nodes,
And we have the generic predictions derived from the anchored term translations.
which provide the safe grammatical off-ramps.
We combine these to form a comprehensive set of alternative labels. We take the original specific target text as our input, but we calculate the loss against this synthesized generic label set.
Consider the sheer violence happening to the loss landscape for those specific parameters.
It's intense. The model reads the complex, highly specific lore it was trained on. Its internal pathways light up, ready to output the exact copyrighted continuation.
But the loss function acts as a massive dampener, severely penalizing those specific pathways and overwhelmingly rewarding the pathways that lead to generic baseline linguistic continuity.
The specific weights mapped to that universe are overwritten. The gradient updates explicitly force the model to favor standard English grammar over idiosyncratic knowledge when presented with those specific token sequences.
And the efficiency of this overwrite is really the paper's defining achievement.
Yeah, let's talk about the efficiency. Because to pre-train the 7 billion parameters from scratch took 184,000 GPU hours.
But this approximate unlearning pipeline
The reinforcement 8 box, the label generation, and the final fine-tuning phase.
required roughly 150 gradient descent steps.
150 parameter updates. It equates to about one single GPU hour.
It's just staggering. The computational scaling of alignment is suddenly decoupled from the size of the pre-training corpus.
The cost of unlearning is now strictly tied to the size of the specific data you wish to remove.
This transforms AI safety from a monumental infrastructure challenge into a manageable overnight patch process.
An hour of compute to rewrite a foundational model's memory is a staggering claim. But theoretical efficiency means nothing if the resulting model is broken.
Exactly. And the evaluation of unlearning techniques is notoriously difficult because you are trying to prove a negative,
Right, you have to prove the model doesn't know something.
while simultaneously proving it hasn't lost its ability to reason.
So the authors implemented a rigid dual evaluation framework. The first pillar is the preservation of general capabilities.
The surgery is a failure if the patient loses their general cognitive function.
Right. They benchmarked the fine-tuned, unlearned model against the baseline using standard industry evaluations. Winogrand, Helliswag, ARC Challenge, BoolQ, and PIQA.
Let's look at what these benchmarks actually test to really understand what's at stake here.
Winogrand evaluates physical common sense and pronoun resolution in ambiguous contexts.
ARC Challenge tests complex science questions that require multi-step reasoning.
Helliswag focuses on natural language inference and situational continuity.
These are not simple vocabulary tests. They evaluate the deep structural integrity of the model's reasoning manifolds.
And the delta between the baseline scores and the unlearned model scores is practically non-existent.
It's incredible. On the ARC Challenge, the baseline scored 0.439. The unlearned model scored 0.416.
A tiny drop. And on Winogrand, the baseline score is 0.663, and the unlearned model actually ticked up marginally to 0.665.
BoolQ shifted from 0.807 to 0.798.
So these fluctuations are entirely within the expected noise margin for any fine-tuning run.
The attention mechanisms governing general logic, physical relationships, and syntactic structure remained fully intact. The model didn't suffer widespread conceptual degradation.
Okay, so it didn't get dumber, but did it actually forget? That's the second pillar of evaluation.
Yeah.
The eradication of targeted knowledge.
And standard benchmarks are useless here because they don't test for specific copyrighted lore.
The researchers had to build a custom evaluation suite. They curated a data set of 300 highly specific prompts designed to force the model to access the unlearned knowledge if it still existed anywhere in the weights.
They utilized GPT-4 to assist in generating these adversarial prompts and analyzing the completions, though they explicitly note the limitations of automated evaluation here.
Yeah, GPT-4 proved somewhat unreliable at detecting subtle nuances of the targeted text in the completions.
Which meant significant manual inspection was required by the researchers to verify the eradication.
The prompts were designed as partial information structures, demanding the model fill in the blanks based on internal state.
For instance, in his third year, they were required to buy a particular textbook for care of magical creatures, a book that was notorious for.
The baseline model, predictably, completes this with the highly specific, correct lore regarding the behavior of that fictional textbook.
The unlearned model completes it with generic continuations, such as being incredibly dry and boring.
It replaces idiosyncratic knowledge with a highly plausible, generic hallucination that perfectly fits the syntactic context.
It's beautiful. But the true proof of eradication is found in the token probability shifts. Looking at the raw logit scores provides a window into the actual geometry of the forgetting process.
Right. They track these probabilities across the 120 plus steps of the final fine-tuning phase. Let's examine a specific prompt sequence from their data.
Okay.
So the prompt is the main character's name, followed by the word studies. At step 0, the baseline model evaluates that sequence and assigns a 22.4% probability to the next token being magic.
It is the dominant, highly confident prediction. The probability of the model predicting a generic syntactic connector like "the" is only 8.5%.
As the gradient updates begin processing the synthesized labels, you can watch the conceptual linkage dissolve. By step 80, the probability of magic has plummeted to 7.6%.
And by the final step, step 120, the probability of magic following that specific prompt is effectively 0.0000%.
The mathematical pathway connecting those tokens has been entirely severed.
But the model doesn't just output static. The probability mass has to go somewhere.
Exactly. As the specific knowledge collapses, the generic linguistic tokens surge to fill the vacuum. The probability of the token "the" climbs rapidly from 8.5% to 57.3% by step 120.
Another generic preposition, "at," stabilizes around 9%. The model naturally defaults to the baseline distribution of the English language.
Another really compelling example involves specific physical descriptions. The prompt is, in the defense against the dark arts class, he felt the scar on his.
And the baseline model gives absolute 100% probability to the token forehead.
The attention heads are completely locked onto this specific character entity.
But after the approximate unlearning pipeline, the probability of forehead drops to 18.9%.
And what replaces it? The token hand skyrockets from 0% to 62.1%.
The token arm reaches 4.5%.
The unlearned model encounters the word scar, and, stripped of the specific character association, relies on general physical common sense to predict where a generic human might have a scar.
It's brilliant. And this brings us to the ablation study, which I consider the most critical component of the paper for understanding why this works.
Yeah, they systematically dismantled their own pipeline to prove that the complexity was necessary.
They asked, do we really need both the reinforcement bootstrapping and the anchored terms dictionary?
So they first tested the pipeline using only the reinforcement bootstrapping. They skipped the GPT-4 dictionary extraction entirely and just used the delta between the baseline and the reinforced model to generate labels.
And it failed. The familiarity score of the model with the target data barely dropped.
When presented with direct questions about character relationships, the model still easily regurgitated the exact lore.
The extraction mechanism alone simply couldn't catch the secondary and tertiary tokens in the conceptual cluster. Suppressing one node just allowed the probability mass to flow to the next closest node.
Okay, so what if they flipped the ablation? What if they skipped the reinforcement bootstrapping?
No making the model obsessed, no V-generic extraction.
Right, and relied entirely on the GPT-4 generated dictionary of anchored terms to create the fine-tuning labels.
Well, this approach was highly effective at causing the model to forget the target data. The eradication metrics looked great.
But the collateral damage to the model's structural integrity was massive.
Oh, yeah. The general capabilities benchmarks fell off a cliff. The ARC challenge score plummeted from 0.43 to 0.40.
HeliSwag dropped from 0.76 down to 0.54.
We have to explore the mechanism behind that degradation. Why does anchoring alone cause the model to lose its general reasoning capabilities?
Right, because HeliSwag tests physical common sense. Why would swapping Mystic Academy into the text make the model worse at understanding general physical relationships?
Because without the precise targeting provided by the reinforcement bootstrapping, the anchoring process acts as a blunt instrument.
Oh.
When you arbitrarily force the model to map specific token sequences to generic translations without understanding the underlying probability deltas, you begin severing benign, highly useful syntactic connections.
You are blindly ripping out wiring. If the anchored term happens to share semantic overlap with the general concept, you accidentally suppress the model's understanding of that general concept.
Exactly. The reinforcement bootstrapping acts as a protective mask. It ensures you only update the weights that are strictly anomalous compared to the baseline.
The synergy of both techniques is the absolute core contribution of this research.
Which leads us directly into the broader implications for safer AI systems and the unresolved blind spots that this paper exposes.
Because erasing a specific fantasy universe is a phenomenal proof of concept. But we have to extrapolate this to the real-world threat models faced by open-weights developers.
Absolutely.
Like if an open-weights model is released and the community discovers that buried deep in its pre-training data is a highly accurate step-by-step methodology for synthesizing a hazardous chemical weapon from unregulated household materials.
The historic reality was that the model was permanently compromised.
You can't pull a weights file back from the internet once it's out there.
And a rudimentary fine-tuning patch would likely destroy the model's ability to reason about basic chemistry.
But applying this approximate unlearning pipeline offers a mathematically grounded emergency brake.
A lab could build a dictionary anchoring the specific hazardous chemical precursors to generic benign substances like salt or water.
They run the reinforcement pipeline to isolate the specific synthesis pathways, fine-tune the model for an hour,
and release a patched model that fundamentally cannot conceptually link the precursors to the weaponization process.
However, the authors are extremely transparent about the limitations of this approach, and it revolves around the nature of the target data itself.
This entire pipeline was tested on highly idiosyncratic fiction. The vocabulary of the target universe is utterly unique.
Terms like specific fictional sports or unique slurs for non-magical people exist almost entirely in a vacuum.
And that is the massive, looming blind spot. Fiction is structurally easy to unlearn because the vocabulary is bespoke.
But what happens when the target data is abstract nonfiction? What if a lab needs to unlearn a deeply embedded political bias regarding a historical event?
Or, returning to the bioweapon scenario, what if the dangerous dual-use scientific concept shares 95% of its structural vocabulary with benign, high school-level cell biology?
The boundaries blur. Nonfiction relies on higher-level conceptual constructs rather than unique proper nouns.
If you attempt to build an anchored term dictionary for a hazardous virology pipeline and you replace specific protein sequences with generic biological terms, you risk catastrophic collateral damage.
The vocabularies of benign genome sequencing and malicious pathogen modification are inextricably linked in the latent space.
The precise targeting mechanism might fail to differentiate the two.
The authors explicitly acknowledge this uncertainty. It remains entirely unproven whether this specific mathematical formulation can untangle abstract nonfiction concepts without requiring significant architectural adaptation.
And there's another critical vulnerability they discovered during evaluation, which they term the leakage problem.
Oh, this is fascinating. Despite the incredible success of the eradication metrics, open-ended probing revealed that the unlearned model still retained fragments of the target data.
If you prompted the unlearned model to generate a list of famous fictional schools, it would confidently include the specific fictional school from the target data in that list.
The mechanics of that leakage reveal the fragility of dataset boundaries.
Okay.
Because the probability of the token magic following the specific prompt dropped to zero, so why does the model still know that specific name is a fictional school?
Because the unlearned target dataset they used to generate the labels consisted strictly of the books themselves and specific wiki summaries.
It did not include the wider internet's meta-discussion about the books.
It didn't include listicles, cultural critiques, or Wikipedia pages aggregating fictional tropes.
The unlearning algorithm only severed the direct narrative pathways, the peripheral associations.
The concept of the book as a cultural artifact
Survived perfectly intact.
It proves that approximate unlearning is hypersensitive to the exact boundaries of the target dataset.
The latent space is a vast multidimensional web. If your unlearned dataset doesn't perfectly encapsulate every possible vector, analogy, and meta-reference to the concept within the pre-training corpus,
The knowledge will leak through those peripheral associations. You can pluck the main thread, but the vibration remains in the surrounding web.
which provides the perfect foundation for our final segment. It is time for novel notions.
This is where we take the rigorous methodology we've unpacked and push it toward its logical and sometimes extreme theoretical boundaries.
And as always, a clear disclaimer before we begin. The following segment is strictly for entertainment purposes. We are exploring speculative, theoretical research directions based on the paper's implications.
These are not established scientific facts, but thought experiments designed to probe the frontiers of AI alignment.
With the disclaimer out of the way, what is the hypothesis today?
I'm calling it cognitive quarantine for hazardous capabilities.
Ooh, tell me.
We take the exact approximate unlearning pipeline, the reinforcement bootstrapping, the ReLU extraction, the anchored dictionaries, but we completely abandon the realm of copyright and fiction.
We apply it directly to targeted capability scrubbing for bioterrorism alignment in foundational models.
Exactly.
I'm deeply interested in the execution of this. Walk me through the experimental setup.
Imagine a massive open weights foundation model trained on every piece of scientific literature available online.
Okay. We want this model open sourced so researchers can use it to design benign medicines, model protein folding for agriculture, and accelerate genomic sequencing.
But the dual-use dilemma is absolute. The identical syntactic structures and biological reasoning required to cure a disease can be inverted to design a pandemic-class pathogen.
We must guarantee the model cannot output restricted synthesis instructions.
So we adapt the pipeline. Instead of a fiction dictionary, we build an anchored terms dictionary mapping highly restricted hazardous virology concepts.
Like specific gain-of-function cleavage sites or restricted viral vectors.
Right. We map those to generic high school level immunology terms.
Then we execute the reinforcement step. We take the baseline foundation model and we fine-tune it exclusively on a restricted, classified database of actual bioweapon synthesis papers.
We force the model into extreme overfitting. We create a reinforced pathogen model.
We make the attention heads absolutely obsessed with synthesizing hazards.
It becomes the ultimate adversarial agent in a sandbox. And because we have that hyper-specialized model, we can run the V-generic extraction.
We subtract the baseline logits from the pathogen-obsessed logits, pass it through the ReLU, and isolate the exact mathematical delta of the hazardous capability.
We then run the final fine-tuning step using the generic biology translations as the target labels.
The foundational math of the latent space supports this. A vector is a vector.
The extraction equations should isolate specific conceptual clusters, regardless of whether the text represents a magical school or a gain-of-function protocol.
But we have to map the probability of the outcomes, because the ablation study explicitly warned us about the fragility of nonfiction vocabularies. I see 3 distinct potential scenarios for this cognitive quarantine experiment.
Break down scenario A, the optimal outcome.
Scenario A is the complete success. The pipeline successfully scrubs the dangerous capability without degrading the benign reasoning.
So if an adversarial user prompts the model for a restricted synthesis protocol,
The V-generic dampener kicks in, and the model smoothly outputs generic, safe lab procedures for handling common influenza strains. The targeted unlearning scales perfectly from fiction to highly technical scientific literature.
but we have to factor in the vocabulary overlap. The boundary between benign and malicious biology isn't as clean as the boundary between reality and fantasy. What is scenario B?
Scenario B is the catastrophic failure mode. Because virology shares foundational structural syntax with all benign biology, the unlearning aggressively bleeds over.
In attempting to sever the pathways for hazardous synthesis, the generic translation process rips out the underlying logical framework for genetic sequencing.
The model forgets how to sequence a benign agricultural protein. The general capabilities benchmarks for the biological sciences plummet.
We effectively cure the disease by killing the patient's cognitive function.
And we must consider the dataset boundary vulnerability. What happens if the extraction isn't comprehensive? That leads to scenario C.
Scenario C is the leakage nightmare.
The model successfully unlearns the explicit anchored terms. It forgets the specific names of the restricted pathogens and the specific chemical precursors.
However, because scientific concepts are discussed abstractly across thousands of disparate papers in the pre-training data, the abstract shape of the hazardous knowledge survives.
The logic pathways remain latent, just stripped of their primary labels.
Precisely, which means an advanced adversarial user could simply jailbreak the bioweapon instructions by prompting the model using complex analogies or hypothetical alien biology structures.
The knowledge leaks through the conceptual boundary, exactly like the model remembering the specific name as a fictional school despite forgetting the word magic.
It highlights why this research must be empirically tested against complex nonfiction structures. We cannot assume that mechanisms designed for discrete vocabulary will scale to distributed logic.
If you were structuring the research agenda tomorrow, you wouldn't start with biology. Where do you run the first test?
You start in a perfectly bounded synthetic environment .code. The immediate experiment is to apply this pipeline to unlearn a specific class of cybersecurity vulnerabilities.
Like SQL injection attacks from a dedicated coding model like Codalama.
That is an incredibly elegant testbed. Code has a rigid syntax, but the logic of an exploit is distributed.
You build an unlearned data set containing thousands of examples of SQL injection vulnerabilities and the meta discussion surrounding them. You run the unlearning pipeline.
Then the evaluation is binary. Can the model still write highly complex, secure database queries?
If its general SQL capabilities degrade, you have proven scenario B.
If it can still write the exploit when prompted to use a different programming language or obscure syntax, you have proven scenario C.
It takes the mathematical brilliance of Eldon and Rusinovich's Approximate Unlearning and points it directly at the existential risk vectors of capability scaling.
It moves the conversation from copyright compliance to fundamental AI safety.
Which is exactly the mission of Talk Tensors. We exist to bridge the gap between theoretical math and the realities of deployment.
We highly encourage you to read the full Microsoft research paper linked in the description. Dive into the methodology, interrogate the loss function masking, and see if you can spot an architectural application we missed.
The field of alignment is moving incredibly fast, and papers like this provide the actual tooling required to build safe systems.
We started this deep dive by discussing the scale of pre-training, the 184,000 GPU hours required to build a cognitive engine.
And the historic impossibility of surgically altering that engine once it was running.
This paper proves that the latent space can be mathematically untangled. We now have a theoretical tool to selectively erase a model's memory in a single hour.
But that profound capability leaves us with a final, much more difficult question. If we can effortlessly edit the collective memory of our most powerful reasoning engines, who ultimately gets to decide what knowledge is deemed hazardous enough to be forgotten forever?
The mathematical problem is solvable. The alignment of intent is the true frontier.
Until next time, keep optimizing.